Greetings viewers, I am Karthik Vyas and with me I have Arav and we shall be explaining this project to you. First of all, I shall start by explaining the meaning of word epizoology and predation. Predation. In this process, predator hunts prey. For example, a tiger hunts deer and another example is a shark hunts fishes.
Epizoology. Epizoology is an event in which a large widespread diseases occur among non-human population, namely animals. This not only affect the contaminated population but also affect whole of the ecosystem. We observe that during the corona pandemic, we humans suffered with unpredictable circumstances. But as we humans got caged inside our house, the animal life grew in prosperity, and each morning when we woke up, we heard large number of birds chirping. And when I went for a trip in a forest area, I observed more number of animals than what I saw the last time. This made me wonder how this cycle works and what would have happened to animal population if they were caught up in a virus similar to COVID. बराबर है?
Now I shall continue and explain the problem. So basically, we in future are going to face the problem of animal extinction. So in order to resolve that, we are making a we are making a model that explains the decreasing rate of population of animals due to different circumstances, and we are going to observe differential calculus in the decrement of population of animals. Now I shall explain the SIR model. SIR model is a model used to explain spreading of virus in the vast population of animals. S of t. It is the number of susceptible animals at any time t. Now let's discuss on the finding time dependency on S of t. By basics of maths, we can understand that more the number of susceptible, more the chances they get infected, and it is also depends on the negative of infectious animals. Now, the overall equation is as shown. Now, I will start finding the time dependency of R of t. The rate of recovery is dependent on the rate of infected animals as described. In this, B is parameter of animals getting recovered. Now, let's find time dependency of I of t. Basically, I depends on two factors, S and I. And to remove the proportionality, we add a constant. But at least we have to subtract recovery rate from infectious rate. And we get the final equation as shown, and now we can observe the graph. So basically this graph shows us that these now we shall continue and start with our SIR model with natural deaths and deaths due to virus. In this I am going to explain the time dependency of S. In this we are assuming the population to be constant, therefore the rate of death and birth is mu. In this equation, we can see that only one term is positive, which is multiplied with mu. It is the factor of newly born species which are susceptible, and two are negative, in which one is introduced above and one in which is susceptible but will die due to natural cause. Now I am going to explain the time dependency of I. In this equation, we have to subtract the factor which is number of animals that die due to natural death, so it will decrease the rate of infectious animal. Now, the final equation is, now I shall start explaining the time dependency of R. In the equation, we have to reduce a factor in which the animals that die due to natural death are not considered in recovered. Therefore, the final equation is as shown. Now, as we can see, the graph of susceptible starts with above and is decreasing. The new topic is SIR with variable population. In above equations, we assume that the population is constant. Now let's consider the death rate and birth rate to be mu1 and mu2, and we can see this equation. Now by integrating this equation, we can get the separate the SI and R equation as shown in this. We can see that N1 is coming extra and N1 is total population at t is equal to 0. Now we'll start the SIR model with vaccination. Now we are getting a differential equation of vaccination where here K is the rate of vaccination. For example, let's consider out of 10k animals, 500 were vaccinated. Then we can define that the rate of vaccination is 500. The final equation of the following differential equations we get is as shown.
We shall be representing this model in form of differential equation. In the shown differential equation, prepopulation x is prepopulation and y is predator population, and alpha and beta are birth rate and death rate respectively. And similarly in predator population, delta and gamma are birth rate and death rate of predator. We can observe that in prepopulation equation, if population of predator is 0, then population of prey would increase exponentially until and unless availability of nutrition is taken into consideration. But if suddenly prey extinct, the predator population would decrease hypothetically and even extinct. Connection between epizoology and predation. By definition, both these topics are different, but in suit, both are deeply correlated, as virus would affect prey or predator, or even both. So, we shall explain this in two different possibilities. Possibility 1. In first possibility, we shall consider that predator won't be affected by virus. Hence, the predator population shall not be affected directly, but indirectly that will be affected, as the population of prey would decrease. By applying calculus, we obtain this new equation as shown on the screen, where mu1 and mu2 are birth rate and death rate, and k is vaccination rate. Probability 2. Here, we shall consider that predator is susceptible to the virus and may be contaminated by it. Now, as prey was already susceptible to the virus, its differential equation won't change. But now, as predator is also susceptible to the virus, its differential equation will also be changed. The new equation is shown on the screen. Solving the maths. As we observe, there are so many equations with so many variables in SIR model. To have a better understanding, we are using Python code to derive graph of this equation. By observing graph, we can say that susceptibility animals are decreasing, more and more animals getting recovered, hence immune, and some are getting infected also. Infected people are also decreasing exponentially as rate of recovery is high, and of course, recovering rate is increasing. Considering natural death and death due to virus, we get new graph as shown. In this graph, we can observe that susceptibility decreases at a greater rate than what of the previous graph due to the factor that natural death are considered in this figure, and similarly rest of the parameter with different slope are seen in the graph.
Now we shall start the study of SIR equation with variable population by using Python code and observe some graphs. The susceptible changes slowly as the population is not constant and is variable. The recovered population increases rapidly and infected is increasing fast. The infected starts to increase and then decreases as animal decreases. Now we will solve the SIR model with vaccinations by using Python code, that is by showing the graphs. The graph tells us about 5 variables. In this graph, we took vaccination rate to be constantly increasing and it should be above recovered graph, as we can see clearly in the graph. The susceptible people starts from an initial value and then it fluctuates in value up and down slowly because the infected population is also fluctuating. The recovered population increasing gradually due to constant vaccination of people. The disease population increases and then decreases due to people dying from starts and from decreasing and is only affected by natural deaths. As you can see in the graph, the green shows the recovered, red shows the diseased, yellow shows the infected, blue shows the susceptible, and purple shows the vaccinated. Now we shall start explaining the predator-prey model by using graphs. The graphical representation of this model often shows oscillations over time resembling periodic cycles. When prey population is high and predators populations low, predator eat prey, and hence its population decrease and predators population increase. And when prey's population decrease, predators population also decreases, as it will have nothing to eat. Because here we assumed that it has the only source to eat. Now we will solve the connection between epizoology and the prey predator model by using some absolute graphs and using Python code. These are the differential equations, and by solving these differential equations we will get these graphs, which is extremely complicated as we can see. The susceptible starts decreasing because of infected animals starts increasing rapidly and also due to vaccination of susceptible prey. The infected animals started from a particular point and at first increased rapidly due to low recovery rate and decreased death rate of infected animals, and then decreases because recovered people increases gradually. The recovery rate is pretty slow from the start and then started increasing pretty fast because recovery rate increased. As we can see that susceptible the same as shown as shown in the previous slide. The new is vaccinated and the total population X, which shows the complicated graph. The death rate increased gradually. The vaccination rate depends on vaccination rate per day and total population of prey. So vaccination first increased fast and then increased slowly. The predator population rate at first increased because prey population was high at first and then decreased due to spread of virus among prey, and then again increased due to recovery rate of prey started increasing. The prey population rate at first decreased very fast due to spread of virus and then increases slowly due to infected animals started decreasing. Now our project is going to conclusion. Conclusion. When a virus is incorporated into a prey predator model, it brings in complexity to the dynamics, giving us a deeper understanding of how different is their interaction. In this model, we looked at types of prey, infected, recovered, and vaccinated, and predators too, and a virus that affects the prey populations. Impact of virus on prey dynamics. The presence of the virus has an impact of dynamics of prey, causing fluctuations in the number of infected and recovered individuals. Vaccination plays a crucial role in controlling the spread of the virus among prey, reduces its impact on susceptible individuals. Now, interaction between prey and predators. The interactions between predators and prey remain at the core of this model. Predators have an influence on the dynamics of infected prey. Predators can be indirectly affected by the virus through consuming infected prey, leading to changes in their population. We should study complexity in dynamics. Combining virus dynamics with predator-prey interactions adds complete complexity to this model. It reflects real-world scenarios where ecological systems are influenced by many factors. The effect of vaccination. Implementing vaccination for both predator and prey offers a method of disease management. Vaccination aids in diminishing the transmission of viruses and minimizing the consequences of prey population. Now we shall study dependency on sensitive parameters. The model's behavior is influenced by parameter values. Even slight modification in parameters like birth rates, mortality rates, and interaction strengths result in outcomes. Population resilience. The model demonstrates the resilience of population over time, with the potential for recovery and stabilization, particularly when effective vaccination strategies are implemented. Implications. Understanding the dynamics of virus in predator-prey systems is essential for our ecological conservation and disease management. The model highlights the intricate relationship between species and the potential consequences of introducing external factors such as infectious disease. Let's consider future consideration. Future research could focus on refining the model based on empirical data and exploring additional factors such as spatial dynamics, evolving virus strains, and the impact of environmental changes on ecological interactions. These would provide a more comprehensive understanding of the dynamics of virus infected populations within ecological communities. So, this was the project conducted by us, the group Calcrafters. Thank you.